All right, let's look at the question from discussion question 5. So we have this RLC circuit. So a circuit that contains single inductor, single resistor, single capacitor, all in series with a voltage source. So this is a homogeneous equation. So effectively what we're modeling is a voltage source that does not, it doesn't have any it's not imparting any voltage. So it's effectively voltage equal to zero. So we are given, basically a template for this equation um, that models this circuit. So let's go ahead and first write this equation based on the component values we're given. So I'm focusing on this LQ double prime plus RQ prime plus 1 over C times Q equals 0. So L is the value of our inductor in henries. So that's 100 milliohm or sorry, millihenry inductor. So all in other ways is a tenth of a henry. So 0.1 Q double prime plus R times Q prime. So what's our resistance? R is 1,000 plus 1,000 Q prime plus 1 over C. So C is a microfarad. So plus 1 over 10 to the negative 6. So yeah, micro is a millionth. So 1 over 10 to the negative 6 times Q equals 0. We can clean things up a little bit. So 0.1 times Q double prime plus 1,000 Q prime plus, I'll just keep it as 10 to the 6, but it's effectively a million. Q equals 0. I would rather work with an equation where the coefficient of Q prime is just 1. So I'll multiply everything by 10. Doing that gives me Q double prime plus 10 to the 4th Q prime plus 10 to the 7th Q equals 0. So here is my differential equation. So this is going to be the thing that I'm going to deal with for this discussion question. So now I want to solve this equation. So I'll go ahead and stay on this slide. Solve this equation given initially no charges flowed to the circuit. So just to remind us, what does Q stand for? Q stands for the amount of charge in coulombs that have flowed through this circuit at time t. So we're told that Q of 0 equals 0. What else are we told? And there's initial current of 20 milliamps. So another way to think about current is it's a rate of change of charge with respect to time. So that initial Q prime of 0 is 20 milliamps or 0.02. All right, so now I have a second order homogeneous linear differential equation. I have two initial values. I should be able to, get my complementary solution now, including the values of the unknown constants I'm about to get. So, how do I get my complementary solution? Well, that always comes from the characteristic quadratic. So in this case, that'll be r squared plus 10 to the 4th r plus 10 to the 7th equals 0. I don't think this factors, so let's go ahead and go to the quadratic formula. So r equals negative b, negative 10 to the 4th, plus or minus the square root of b squared. So 10 to the 4th squared is 10 to the 8th, minus 4 times 1 times 10 to the 7th. So minus 4 times 10 to the 7th, all over 2. So I get two real roots, negative 10 to the 4th plus or minus 10 to the 8th. While we're at it, let's actually get a value there. And let's approximate it. So 10 to the power of 8 minus 4 times 10 to the power of 7. So I get 60 million. What's the square root of 60 million? About, let's round it to the nearest whole number. I get 7,746. So negative 10 to the power of 4 plus or minus 7,746 all over 2. So R equals, so 10 to the 4th is 10,000. So negative 17,746 over 2. And also, what's 10,000 minus this? 2254 minus 2254 over 2. So one of my values is going to be negative 1127. Another one of my values is going to be what? 17746 divided by 2, 8873, negative 8873. So these are my two values of R. All right, so what does that tell me so far about my equation? All right, so these two rates here, these are going to give me basically my complementary equation. So, or this is a homogeneous equation, so the complementary solution is the only one I'm looking for. So C1 e to the negative 1127t plus C2 e to the negative 8873t. Now, do I have enough information to figure out what C1 and C2 are? So I do. Kind of running out of room, but here we go. So I know that Q of 0 is equal to 0. So what happens when I plug in 0 for t? I'm going to effectively get C1 plus C2 equals 0. So I know that C1 and C2 are exact opposites of each other. So now, to use my another initial condition, I need to take a derivative of t. So that's going to give me negative 1127. Get rid of this check mark. C1 e to the negative 1127t minus 8873 C2 e to the negative 8873t. Now, what happens if I plug in 0 to that derivative? I get negative 1127C1 minus 8873C2, and that equals what? 0.02. So I'm going to rely on the fact that I know that C1 equals negative C2. All right, so now that I've realized that C1 equals negative C2, I can go ahead and apply that relationship here. So I'm going to go ahead and say that 1127 C2 minus 8873 C2 equals 0.02. So let's go ahead and do a little bit of algebra, figure out what C2 is. So 1127 minus 8873 gives me negative 7746. If I divide 0.02 by that, I'm going to get something really small. Okay, so let's capture this in scientific notation. All right, I'm getting that C2 equals negative 2.58 times 10 to the negative what? Let me count. Times 10 to the negative 6. Okay. So that should allow me to write down my full equation now. So Q of T is equal to, actually, in the interest of space, here's what I'll do. This C2 that I found, let's just call this thing A. And that way I can kind of condense some things. Q of T is equal to negative A e to the negative 1127t plus A e to the negative 8873t. All right, so that should be my answer for number 1, number 2. All right. So before I go to our new slide, so I get, actually, let's go ahead and do that, and then I'll remind myself of my equation. Or actually, number 3 is going to call for something different. Question 3, your previous solution contained 2 exponential terms with different decay rates. Modify the resistor value so that there is only one distinct decay rate. So why would that happen? So here's essentially what we're trying to do. So we're not given any, we're not told to change what the values of the inductor and the capacitor. So I will keep those. So what's our inductor was essentially 0.1 henries. So 0.1 Q double prime plus R Q prime plus 1 over C, which ended up being 1,000,000. Q equals 0. Now we want to dial in this R value so that I only have so instead of having R1 and R2 that are like distinct, I essentially want R1 and R2 to be identical. So why would that happen? So that happens when this quadratic that comes out of this, like my characteristic quadratic here, only has one distinct solution. So why would that happen? That's going to happen when the discriminant is equal to 0, or effectively, the expression underneath the square root is equal to 0. So basically, I'm going to try to, this is kind of like when we were doing finding bifurcation values. I'm trying to find the bifurcation value of this R. So let's do that. B squared minus 4AC. That's going to be equal to R squared minus 4 times 0.1 times 10 to the 6th. And I'm going to set that equal to 0. So R squared is going to be equal to 0.1 times 10 to the 6th is the same as 10 to the 5th. So R squared equals 4 times 10 to the 5th, so that's 40,000. Which means that R is going to be equal to the square root of 40,000. Let's find that. Oh, comes out to be 200 ohms. So R equals 200 ohms. So that's our new resistor value. So now that we have that, we're going to solve our new equation. So let's write our new equation. So 0.1 Q double prime plus 200 Q prime plus 1,000,000 Q equals 0. I'd rather deal with the first coefficient being 1, so I'll multiply everything by 10. So Q double prime plus 2000 q prime plus 10 to the 7th q equals 0. I could do quadratic formula on this, but hopefully, like based on what I just did with the discriminant is, oh, hold on. I did not multiply by 10. 2000 q prime. So what I should have here is this. This should have come out to be this. So r squared plus 2000r plus 10 to the 7th equals 0. This should be a perfect square. And it should be specifically r plus 1000 squared, or I'll write it like this first. All right, now that I'm looking at this, this will not work, because if I were to FOIL this out, 1000 times 1000 is not 10 to the 7th. So let's go back and debug. If I look at the discriminant again, r squared minus 4 times 0.1 times 10 to the, so yeah, 4 times 10 to the 5th. That is not what this is. Okay, so we're gonna throw this out. This should be r squared equals 400,000. So what's the square root of 400,000? Oh, would love to have a convenient value like 200 ohms, but let's do this right. 400,000. Square root of that is 632.4 ohms. So let's throw all this stuff out. And start again. So now we have found the true resistance value. I'm gonna go ahead and just call it R, so I can keep it exact until I need to round it. So R is the square root of 400,000. So 0.1 Q double prime plus R Q prime plus a million equals 0. Go ahead and multiply through by 10. So Q double prime plus 10RQ prime plus 10 to the 7th equals 0. So again, based on the way I've done this, having second thoughts here, maybe this would be easier if I just dropped in this value. So 10 times R would be 6,324. Right. So based on what I did with the discriminant, I was looking for that bifurcation value of R. So this should be a perfect square now. Specifically, it should be Q minus whatever half of this is. So what is half of 6324? And I know I'm rounding a little bit, but we'll take that into account. So this should be 3162 times itself, essentially. So if we were to expand this, would this get us back to where we think we're going to be? So we know that 3162 times 2 is 6324. That's how I got this value. But let's just be sure. What is 3162 times 3162? It is 9,998,244. So very, very close to 10 million. So, you know, aside from the rounding error that we introduced, I believe this is fine. So we have R1 equals R2 equals 3162. So what does that mean about our complementary solution? When my, you know, R values are the same, what do I do? So here's what we're going to do. Q of T, now let's give myself a little more space. Q of t is going to be equal to C1e. Oh, by the way, huge mistake here. These need to be plus because these need to be R1 equals R2 equals negative 3162. So C1e to the negative 3162t. But what does the other one look like? So when we have like interaction between the two components of the complementary solution, or any two components of your solution, that's where we have to multiply by a power of t to actually make the solutions distinct. So C2TE to the negative 3162t. So this is our, like the form of our complementary solution. So now we still have the same initial conditions. We still know that Q of 0 equals 0. So when I plug in 0 for t, what do I get? I get C1, and then I get plus C2 times 0. So in this case, I get that C1 equals 0 for free, which is kind of nice. That means that I know that my first term that I thought was going to be part of my solution is not going to be part of my solution at all. We still got to find a value for C2. So the way we do that is by taking the derivative, Q prime of t is equal to negative 3162 C1 e to the negative 3162t. And then this other term is going to require the product rule, plus C2 e to the negative 3162t minus 3162 C2t e to the negative 3162t. So what does Q prime of 0 look like? Well, if I plug in 0 to my first term here, that's going to give me negative 3162 C1. The second term is going to be plus C2. And then this third term is going to be 0, because that plugging 0 for t is going to make that term vanish. And I remember that my initial current, my initial Q prime, was 0.02. I also get C2 for free because I can rely on the fact that I found that C1 is equal to 0. So I get the C2 is equal to 0.02. So in this case, the solution is Q of t equals 0.02 t e to the negative 3162t. And that is the answer for 3. All right. Let's go ahead and get our new sheet for question 4. Now I want to replace the resistor with a wire. Basically, effectively what I'm doing here is that R equals 0. So what effect does that have? So now my equation is LQ prime, so 0.1 Q double prime. Middle term is gone now. Plus 10 to the 6th Q equals 0. Again, I'll multiply through by 10. So Q double prime plus 10 to the 7th Q equals 0. What does the quadratic look like? R squared plus 10 to the 7th equals 0. Without that middle term, I can kind of just solve this. So R squared equals negative 10 to the 7th. So R is going to be equal to plus or minus, the square root of 10 to the 7th I. So what is the square root of 10 to the 7th? I should have remembered that. Yeah, 3162. Just looked at that number. I'll go ahead and round it to the nearest integer. So plus or minus 3162 I. So what does that mean about what our solution looks like? So we have a totally complex complementary solution. So it's going to look like this. Q of t equals just a reminder, what is e to the it equals what? Actually, let's put it in the margin. E to the it equals this Euler's identity, cosine of t plus I sine t, which is what we're going to rely on here. So what I have is basically e to the 3162 it. And yes, there's a plus or minus, but in these complex cases, since my roots are conjugates of each other, I can look at one of them and get everything I need to know about the complementary solution. So I'll break this down. As with any complementary solution, until I apply the initial values, the constants are just unknown. So C1 times the cosine of 3162t plus C2 times the sine of 3162t. So that's what my complementary solution looks like. So we are told same initial conditions. So what does Q of 0 look like? Well, when I plug in 0 so cosine of 0 is 1, so I get C1. Sine of 0 is 0, so I get that C1 equals 0 again. To go further, I need a derivative. So what's Q prime of t? Q prime of t is equal to negative 3162 C1 sine of 3162t plus 3162 C2 cosine 3162t. Now I plug in, now I plug in 0. Q prime of 0 is equal to, first term vanishes. Second term becomes 3162 C2. And I know that when I plug in 0, I get that current of 0.02. So what do I get for C2? C2 is equal to 0.02 divided by 3162 equals something so minuscule. Where's my cursor? So approximately 6.33 times 10 to the times 10 to the negative 6. So solution to this equation is Q of t equals 6.33 times 10 to the negative 6 sine 3162t. All right. So now I have solved 3 different differential equations. So what do I want to do now? So question 5, as t grows very large, how much charge flows through each of the circuits that you've previously modeled? So now we're looking at basically end behavior. So what happens? Where's my first equation that I solved? Oh, I just didn't box it in. It's down here. So as I let t get very large, what happens to q? So we can think about that. Let's first just think about it qualitatively. So in the equation in the lower right that I've boxed in there, what's going to happen to Q as T gets very, very big? Well, as Q gets very, very big, or sorry, as T gets very, very big, basically I'm raising E to both of those terms, both like to negative terms that are getting, more and more negative as T goes larger and larger. Those are essentially both going to go to zero. So as time goes on, my charge is going to approach zero, which might seem weird because even though I start with an initial charge of zero, I also start with like a positive rate of change of charge. So let's keep on going, even though that might sound totally against what your intuition says. My charge is going to go towards zero. What about this one here? As T gets very big here, this one's not quite as obvious. So I'm going to rewrite this as Q of T equals 0.02T over E to the 3162T. Now, if I look at this, as T gets bigger, both numerator and denominator are going to go towards infinity. They're both going to increase without bound. I'm not going to go through it, but if you want to, you can do it to convince yourself. I could use L'Hopital's rule here to show that the limit here is essentially zero, and that's because basically the denominator grows at a faster rate than the numerator. So this one goes to zero as well. Again, even though I start off with the charge increasing. What happens here? This is a sine wave. So as T gets larger and larger, the charge it has no limit. It's basically just oscillates back and forth, positive, negative, positive, negative. So what's going on here is that charge, electric charge, even though it might not seem this way, it is a vector quantity. It can be negative. That's because I'm sure you all have like different levels of experience and exposure to, electrical engineering, electromagnetic concepts, but there are two different kinds of charge carriers: electrons, which have negative charge, so charge can be negative, and holes, which have positive charge. So I can eventually have a net zero. So in these first two circuits that have decays, the charge is eventually going to settle out to zero. In this final circuit, this is a little bit idealized. This doesn't happen in real life. In real circuits, there's no way to eliminate all your resistance. You're always going to have some. But in this ideal circuit, what's going to basically happen here is whatever current we had flowing through this circuit, it's going to charge that capacitor. And then that capacitor is going to discharge, generate a current, and that current is going to charge that inductor. And that's just going to continue indefinitely. Those two things are basically just going to charge each other back and forth. All right, so that's all for this discussion question.